thing should be recording. Hopefully. Let me just make sure, since I'm using Linux today. Well, it is recording. Let's trust Linux. Good. I hope you guys can hear me well. Today I have a much better voice, thank God. So hopefully I would be a bit better in finishing this lecture today. So let's get started. This lecture today is really interesting, and I think you will like it. Of course, am I getting messages through this thing? I need to get the notifications off. And that's the matter. Well, today we're going to be looking at a couple of basic concepts. Obviously, everything to do with language modeling. Can you share? Did I get that message? 1 second. Let me just bring up the chat here. Can you share the lecture notes for today? I thought I had put them into Moodle. 1 second. Let me just double check. If I didn't, I will add it for you straight away. No, I didn't. You're right. Let me just do that quickly then. Just so some people can follow at their convenience. Yeah, I put the link here, and this one, language models. And you should have it now in Moodle. Good. So you should get access now to the lecture in both places. So let's walk through this thing then. Let me go into slideshow. Maybe a bit more of brightness so I can actually see the lecture notes myself here. And let's fire up. So today we're going to be introducing the motivation for language modeling. You will see it's going to be an improvement over the previous representations of texts that we were looking at before. We're looking at the bag of words representations and vector space and that kind of stuff. So this is a new type of representation based on probabilities. So because of that, we're going to be exploring a little bit a bit of background in probability, which you're going to remember from school, I'm sure. And then we're going to delve into language modeling itself. And then we're going to look at something called smoothing that will make sense later. And finally, the representing documents using language models or probabilistic representation of documents. And finally, we check some things that we can do with this new representation, which is some similarity computations, for example, by this time using probabilities, which is very cool. And you'll see that it's the most common way of doing these things these days. So as a little intuition builder here, we have a language modeling exercise. And you will see that in these two sentences, there are 2 words that make sense and 1 word that doesn't make sense. And we know this because we humans have been trained through all our learning to be able to make some predictions as to what's going to come after a certain bunch of words. No? For example, here, deny D, you would naturally see that probably allegations is fine. It's a good word. It's a high probability, word with a high probability to appear after those 2 words. And you have deny the claim. Claim would be also quite high probability to appear after that. Yes, could be amongst others, no? But deny the sock, probably sock is going to be a word that doesn't appear as much following those 2 words, no? Deny the sock. Who denies the sock? Deny the sock to what? It's a bit more weird, no? Oh, sorry. This is my mouse. My mouse, as per usual, jumping. Similar to that, we have this other word, this other sentence here, no? That was closed. That's probably likely, yeah. That was furiously. It doesn't even make sense grammatically, no? That was furious, maybe, but even that was furious would be weird. That was lit. Yeah, okay, that could be a word that comes after that. Okay. So you see, what I wanted to understand here is intuition, that there is some expectation. You can make predictions as to what the next word can be based on some context, which is basically the task that we're going to be doing, the task for which language modeling was designed. A prediction of a word based on a context. Predicting a word based on a context, or the next word, or predicting as well computing the probability, for example, of a whole sentence to appear given some background text. Right. So as a little joke here. So as I was saying before, humans predict the next word based on learned experience. So we are very, very, very good at this. Most of us, some people, we are some in sync. We are finishing each other's TEDx. That's something that can happen with language modeling. No? If you have really bad language modeling, you don't get the right word that you would expect there. No? It's just a small joke to set up the mood. So in this lecture, what we're going to be doing is looking at ways to using statistics and probabilities in particular to do the same, to predict the next word in sequence, or estimate the probability of a sentence appearing at all in the English language, for example. No? So as I was saying, just reinforcing the idea, what language modeling is about is building a predictive model of language. So that's what I'm talking about, predicting something. Based on language, you are capable of doing predictions. And in the previous lectures, we primarily dealt with an ordered bag of words. So remember the difference between the particularity, about the unordered bag of words, or bag of words, is that we dropped entirely the assumption of any dependencies between the words. So the words are dealt with and are assumed to be isolated from the other ones. There is no way we can use bag of words to make any prediction as to what comes after what. So, for example, we couldn't build what's it called, query suggestion system, for example, suggesting different subqueries when you start typing a query in a search system, no? So the goal of language modeling is, as I said before, predicting the probability of a sentence of words or the next word in a sentence. These are two ways to look at it. There is somebody with the microphone open. If you can, please just go silent, because I'm having some issues with the Teams in the Linux version. I cannot control certain things. So please keep the microphones in silent. Right. So as I was saying, this sort of modeling has a lot of applications, and you can think of many applications yourself. Okay, there's somebody with the microphone open. See if I can cancel it. Okay, that's fine. Right, so there are many applications that you can think of. I'm sure you can think of any other applications as well, but this is just a bunch of them. No? So, for example, the most obvious ones is suggesting text. So you can build, for example, a language model of the most common sentences and words that people talk about in certain contexts. For example, when writing an email or a text message, you can get suggestions for it. Similarly, you see here some assumptions. No, when you have Monday morning at 8, one suggestion based on a language model, based on some knowledge built from sequences of words in English language, you can assume that you could have this word coming after. Oh, we cannot see. You cannot see my screen. Oh, I'm sorry. Thank you. There you go. Back in. Sorry, I had a. Okay. There. There you go. Sorry, guys. I was panicking with the with the microphone open somewhere, and I somehow clicked the sharing screen thing. No worries. You should see it now, right? Is it okay? Perfect. Thank you. Cool. So as I say, this is certain applications, but it's not limited to this, of language modeling. This is why we are interested in this. You can do many more interesting things with language modeling. You can even do machine translation. So you can build a language model of a certain language and the match in the other language, and do certain translations as well when you build knowledge on both language models. Something that is very well done with the transformer architecture that you will explore in later lectures. It's one of the main applications section. But yeah, very interesting stuff. Spelling corrections, you can do that kind of stuff. Text segmentation as well, it can be used in text segmentation because you have knowledge about the vocabularies and the most likely words in vocabulary, so you can make assumptions as to where to split the words there. For example, in this crazy domain name. Let's not focus too much on this. Just to get an idea. So there are many applications you can do, and they are all based on those two tasks, no? On being able to predict a sentence coming after another sentence, for example, or chunk of words, or being able to predict the next word in a sentence, which is that related tasks, right? So let's do a quick review in probability. I'm sure you remember all this from school. So I'm just gonna kind of jump out. I could have asked you to do this exercise, but I think it's quite trivial, so I think you will understand it, no? So the chance of a likelihood, maybe I'm gonna do a quick poll. The chance of likelihood that a particular event will happen. So for example, what would be the probability of that a card drawn here is 8? Can someone give me a quick answer? I'll give you 10 seconds. We have 4 8s. Over. Some super quick answer. 7%. Probably. Probably. So it would be we have 4 over. How many cards do we have here? Is it 52 cards, I think? I'm gonna jump in the next one and see quickly. Whoop. Over 54. Over 52, sorry. So we have 4 8s over 52 possible cards. Probability that a card drawn is red, so that would be 26. So there are 26 red cards out of a whole stack of 52 cards. One thing to have in mind in probabilities is that they have to satisfy, for something to be a probability, and this is important, it has to satisfy these 2 rules. So the first rule, and the most important, is that the values have to be produced have to be between 0 and 1. If they exceed 1 or go under 0, it's not a probability. It's going to be a likelihood, if you ever hear about that in IR, for example. Likelihoods can be above 1 or under 0. Some models produce likelihoods, actually. But most approaches, most models should adhere normally to probabilities between 0 and 1. And you have also another requirement here, and it's that all options should add up to 1 as well. So if you have probabilities of what can I say of red ones here and black ones, the probabilities of being red is going to be about 50% of the cards, and the probabilities for the black ones is going to be another 50%. So it's going to be 0.5 and 0.5, which both add up to 1. So when you have multiple options and you are computing the probabilities for one of the x's or one of the options, if you add all the possibilities for that, all the combinations for that thing that you're trying to measure, all of them should add up to 1. If that makes sense. So again, that example. Red ones are about 50%, 50%, because they have of the stack, and the black ones are 50%, half of the stack as well. So that will give us 0.5, 0.5, or 50% and 50%. Add them both, you get 100%, or what's the same, 1 in this scale from 0 to 1. Right? And then you have these other things. So a joint probability, when something and something has to happen, is treated well like this. So a drawn card is 8 and red. You will see that is an 8 and red is 2 over 52. You combine those two there. You will also see we'll explore other things later. And then conditional probability here, a chance for an event or another event. So this is interpreted and read like this. So the probability of that the card is 8, given that the card drawn is red. So this is important because we're going to be looking at this is talking about the context of this prediction here, no? Of this probability. So the context of this probability is that the card is red. This is why instead of using the whole stack, like in the other probabilities, we are actually using only the red cards. Right? This is the condition that we have here. So probability that the card is 8, given that the cards are red. So the cards are red. There are 26 red cards, and 2 of which are 8. That will be the probability. Similarly, if we do it the other way around, so if probability the card is red, given that the card drawn is 8. So we first look at the 8 cards with 8s. There are 8 cards, and 2 of which are red. So that's 2 over 4. So see, this is a distinction, right? This is an important thing to have in mind. The context here is important. That language here that we use. And this is important because we are going to be doing predictions of certain words. You can imagine this being a word and this being the context of the word. So the preceding text, for example, could be this, and this would be the word to be predicted. That's very important. If you have any doubts with this, let me know. Right. So here we have a few tools. Just a quick revision. So we have a Bayes theorem that is expressed like this, which expresses the probability of something happening given something, and it's can be expressed like this. You have a chain rule for probabilities when something happens and something happens and then something happens and then something happens. So there's 4 things happening, and this can be decomposed in this fashion. So again, remember what I just talked about. So A given all this context, you see here, A given all this context, then the probability for the rest of the context, and then this thing itself is decomposed by the probability of well, we include what we had here before, but see how we decompose this bit here of probability of B, C, and D as the probability of B given C and D, and then the probability of C and D, and then the C and D is decomposed further into the probability of C given D and the probability of D. So we can decompose the whole thing into this expression here. So this is a chain rule. Finally, we have another bit. So A and B are independent if the probability of A multiplied by the probability of B. So this is something to to have in mind. This is independent, and from the Bayes theorem, it follows that then if this is the case, the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. So this is just a little bit of refresher of rules and things. If you want to learn more about it, you can find lots of resources on the internet and that kind of stuff. I just have this in mind for later on. We will do some exercises and stuff, so you will get a bit of practice with the things that you need to know. Cool. So just a little bit more of vocabulary. I'm just building a little bit of vocabulary here so that we can address the next part. So probability distribution, you guys know what a probability distribution is. So it's in a simplistic notion, a probability distribution specifies the probabilities to all possible outcomes of a random experiment. So, for example, I'm going to get you a probability distribution. You know what a probability distribution is. For example, for language. Just randomly going into Google and then showing you a probability distribution of something. Can I get something quick? Just that is a probability distribution, for example. I tried to find something about language, but that's a probability distribution. These are different options that can happen in your model. So imagine this could be frequencies of words or probabilities for words, and this could be the words with the highest probabilities and words with the lowest probabilities, and so on. There are other types of probabilities of throwing dice and having different results, or probability distributions of, I don't know, different events or whatever. You know what probability distribution looks like. So let's now focus more on that. So then we have the notion of a binomial. So this is a binary, when you have binary outcomes. So a binomial model that deals with the binary outcomes, or binomial probabilities when binary outcomes. So you can have either one thing or the other one, or you have then multinomial models or probabilities or distribution, where you have multiple outcomes, like in language. Every single word is an outcome, and that is a multinomial. Just have every single word has an assigned probability, and each word is an outcome. Well, a binomial thing could be something is red or black, or something is higher or lower than 8 here, or that kind of stuff. Something is true or false. Right, so just a quick revision of vocabulary. And finally, we go into language modeling, which is what is going to be very interesting today. So let's describe it a bit more formally, although you already have the intuition from what I've been saying, I'm sure. So I was talking about before, the probability of a whole sequence happening, or the probability of the next word in a sequence. For example, when we try to do a query suggestion, a query, query suggestion, suggesting text for a query, or making suggestions when you're writing text. So this is formally written, expressed as this. So a sentence as a sequence of words here, or the probability of the next word is given the probability of this word k plus 1, so following that word, given this sequence of words, word 1 to k. And just notice that this is a shortening of the actual more proper notation that would be like this, just a bit harder to write. But you're going to see it more like this in this one, and in many, many words. So we save ourselves from writing that, those capitals. Cool, easy to see. So let's have a look at something. So how do we model a language? So as I said before, what we're trying to do with language modeling is to compute probabilities for words. So for words or sequences of words. So it depends on the kind of language model that you build, and we're going to see differences. So what you do is you need to count. What you do is just count the number of times a certain tokens or engrams appear. And you can then normalize that by the total number of possibilities. And that is expressed as in this little function that you see down here. So the probability of a sequence of words in a language model or a word is given by this formula. So it's the count that particular sequence appears divided by the total number of options that appear in your collection. No? And this is what is called the maximum likelihood estimate that you're going to be seeing everywhere from now on, in this lecture notes at least. So that expression here, maximum likelihood estimate. Okay, probability of drawing the probability of drawing this exact sequence from the collection. That makes sense, right? Are we still good? You guys still with me? Okay. I have no interaction with you guys anymore. No one talks to me. Right. So there's still kind of problem here. Oops. Is it bad? Is it just bad quality of the sound or what? That's a static. I'm tempted to do a quick switch to Windows. So yeah, let's actually do it. Since we are I'm just gonna do a switch to Windows, okay? And I'm just gonna restart here quickly on page 13. So I'm gonna terminate this recording. Gonna switch to Windows, see if it deals with it a bit better. I think it's my Linux install is a bit weird. So guys, please don't run away. I'm stopping this lecture right now, but I'll restart it in like 3 seconds, in a few minutes, 1 minute. So see you back. Maybe actually let's take the 5 minutes to rest right now, and we restart at 40 past. Okay. It's very quick. See if it improves things. Perfect.